surprises. That's fantastic. So, okay. So welcome back. This is pseudo lecture 9. If you're wondering when this sort of series will come to a natural pause or stopping point, then I think we're probably 2 or 3 from a natural place to stop, because at that point we'll have really defined absolutely all the major things from which we can do things. So then what I'll likely do is, after deciding for a good place to stop, after doing some examples, I'll perhaps pause, or at least officially stop, and then restart so people can drop off or jump in as they see fit. Okay, so today the plan for this hour is going to be to continue to develop language, talk about schemes. So at this point, we know what schemes are. So schemes, well, they're going to be some ringed space, and it's a ringed space that looks locally like a spec, and we know what specs are as ring spaces. So what do we don't know, there are a lot of questions, like what is a variety, for example? You'd think that would be easier than a scheme. We want to know what maps or morphisms between schemes are, and we don't yet, which means we really want to, and I'm really happy people are asking questions, because it means you're looking for the right, you're feeling the need for something important. So we can't even talk about viral products or really functors of points. But then soon we'll know what the category of schemes is. So that's the plan. And so let me start with some projective schemes, and I'm going to attempt to give an overview that's detailed enough that you'll be reasonably happy, and leave the details for you to read. And so as motivation, we've already talked about projective space, and we built projective space Pn, and there are these things which it's hard to actually really define, but let me just call them projective coordinates. And we have these things x0 through xn, but the local coordinates, when we defined it, were not in terms of these, they were in terms of these weird things that we could think of as quotients of these meaningless things. And so within there, we have examples. Anytime we have a homogeneous polynomial, there's one that's homogeneous degree 8, then it's going to cut out something we've already made sense of it as a scheme, because we can make sense of it in each of our affine patches. So that's our motivation. And the idea that we're gonna is that for any graded ring, we're gonna cook up a scheme or a variety.
So Ravi, we got a request to move your pointer off the screen.
My pointer. That's interesting, because my pointer. Great. Is it this thing? No, I don't know what. I see no pointer, which is slightly disturbing. Let me try this, and then try this, and let me ask. Is there a pointer still there? You can let me know, because I know you're delayed by 20 seconds. Okay, so I'm going to keep talking, and then let me know if the pointer is still there and where it is, I guess. Well, I guess I can look. You know what the danger is, if I play YouTube, you'll.
Oh.
Okay, I'm just going to go on, but let me know.
Well, I'm here. I'm here. If you
okay.
Do you have a question?
Yes, there's an issue with the pointer.
It still there's no pointer, but you're zoomed. Your thing is all zoomed in.
Oh. Better?
Nope.
Nope. Okay, now we found out what the thing is. That was.
Now you're there.
That was good.
Well, the thing is still a little zoomed in. I think you're maybe in the
presentation mode. Yes.
Presentation mode. There you go. That's perfect. Oh, and now there's this thing on the bottom. There you go. That's perfect. That's good. All right.
Great.
No pointer. You're good to go.
Okay, great. Okay, good. So the game is going to be to take something instead of dealing with this equation, we'll work with this graded ring. So rather than with specs, we take a ring and we produce something. We're going to take a graded ring, and we need to say what that is and get a scheme or a variety. And then the one thing I find surprising is that graded rings, they feel like very 19th century and very like they should be the easy thing, and schemes are very fancy in 20th century and difficult. But actually the scheme stuff is going to be easy, and the graded rings can get actually quite confusing and intricate. So that's, so you may or may not agree. But let me define what I mean by graded ring. So a Z-graded ring or Z-graded ring is it's got a bunch of graded pieces graded by the integers. We call it the grading. The elements are called homogeneous elements of degree n. And I should say the example you should have is the polynomial ring or the quotient of the polynomial ring from the previous page. So this isn't meant to be mysterious. And the adding and multiplying with respect to grading, you add 2 degree homogeneous degree n things, you get something in degree n. You multiply 2 things of degree m and n, you get degree n plus n. And so our examples, so long as you mod out by something homogeneous, that should make you happy. Okay, and inside it we have ideals. What kind of ideals do we want? The ideals we want, we'll consider are ones that respect the grading, which are homogeneous ideals. And that might mean, you might think several different, oh, actually, sorry, let me just go back and say one thing back here. I should say, let me just first of all point out that this ring is actually an algebra over the 0th graded piece. And so that's just fairly obvious. That's from the definition. And also here, you could say in this polynomial ring, when you look at this, you probably immediately think the reasonable thing, which I did intend, which is that the degree of each of the pieces is 1. Each of the coordinates is 1. But to be honest, I could have instead made it be I, or maybe even 2I, and then this equation would still make sense. You'd still have a graded ring. So really you have to say what the grading is, but also really, if it's obvious from context, then you should be happy to. But you could have really interesting gradings. You don't have to have very boring gradings. Okay, so then we have the notion of something which is graded in non-negative degree, has the obvious meaning. And then the ideal consisting of things of degree bigger than 0, but is an ideal. It's a homogeneous ideal. And it's called the irrelevant ideal. And the reason it's called that is irrelevant to us, so I'm not going to say why. And so if you have something which is a finitely generated, it's already an algebra over S naught. But if it's a finitely generated algebra, which turns out to be the same as saying that the ideal S plus is finitely generated as an ideal of this graded ring, so then we call it a finitely generated graded ring. And that's the thing we're going to cook up a schema. And just in advance, I'll say, just like with projective space or things cut out by equations in projective space, when it's generated in degree 1, it's going to be nice. Okay, so let me just, before I go on, I made a whole bunch of definitions, so I'd like to go back and look at them again, even though the slides are already visible. So the things I've defined are the notion, let's see, great. Again, there's the notion of a Z-graded ring. You know what a grading is, homogeneous elements. And a homogeneous ideal. I guess I went back before saying that this means anything you might think it means. It's generated by homogeneous things. Also, it breaks up into direct sum of things. Any element of the ideal breaks up into graded pieces. So the homogeneous ideal, it can be non-negatively graded. You have an ideal inside it, S plus, and you have the notion of a finitely generated graded group, which might even be generated in degree 1. So those are the ingredients, those are the words. You can flip back. And now I'm going to tell you what the scheme is. And the scheme is, it's going to be called Proj for making a projective scheme. And actually, we call S naught A, just for convenience. This can also be called projective A scheme. So as an example, why the name? If you're talking about complex geometry, A might be the complex numbers. Okay, so now I will tell you what it is. What Proj is way too fast because you can read, you can look at the details, but I want to tell it to you well enough that you can really see how it works. So it's a scheme. So it's supposed to be a ringed space that locally looks like an affine scheme. So I'll try to tell you everything at once. And what's the reason this gets a little bit complicated is the reason for a lot of different complications today, which is that we've defined schemes as ringed spaces. That's about geometry, and that's like a floppy notion where we're deliberately being not picking an atlas or anything like that. And yet we want it locally to look like an affine. And so that's the algebra side. And somehow communicating between those two is more complicated than it has to be. So let me tell you, if you like algebra, what the definition, reasonable definition should be, which is you'll glue together affine open sets, just like we did for projective space, and we'll do it in a slightly more clever way where we take our ring, we localize at a positive degree homogeneous form, and then we take the 0th graded piece of that. So because we've inverted F, which has negative degree, 1 over F is negative degree, everything else is positive degrees. So we might get new things in degree 0. We take spec of it. And if you parse what that does for projective space, that exactly will suggest that you create things like this, which will look like x1 over x0, where you've inverted x0, and hence you've used that to knock x1 into degree 0. And so that's what it is. And I can even tell you how they overlap. These are like distinguished open sets where F doesn't vanish. So you could do this for F, do it for G. They should intersect with the thing you get when you invert F times G. So that's the algebra picture, and you could try to figure out why everything glues together the way you think. And it does. So here's the ring space picture. I need to tell you what the points are, what the topology is, and what the functions are. So what are the points going to be? I want them to be the homogeneous prime ideals of this graded ring. So they're homogeneous ideals and they're prime. And then I want them not to contain S plus. And if you want, as an example for a projective space, that in P2, if I were to take the ideal x0, x1, x2, and ask what point in P2 that should correspond to, that should correspond to solving x0 equals x1 equals x2 equals 0, but there's no such point in P2. So that's the reason why, that turns out to be the reason why you have this condition. Okay, what's a topology? I need to tell you what the closed sets are. These are just going to be just like before. I just have a bunch of equations, homogeneous equations, ask them equal to 0. Hence, I know what open sets are. And we even have distinguished open sets, and they're not exactly the old definition. So I put a plus here because you take an element an element of positive degree, and you look where it doesn't vanish. And now, before even going on, I'll first go sideways and say that's where here we can make the connection that this open set will be this spec. So really, some hybrid way of constructing this or thinking about it is useful, because you can then check that this is the underlying set of this, and it has the same topology. So a good way to sort of to connect these two is at this step. And then finally, if you like germs that are compatible, then I'll tell you what the stalks are. The stalks at a homogeneous prime P, or a point corresponding to a homogeneous prime P, where you take your ring, you localize, and you take the 0th graded piece. And as I said last time, you get this nutty thing that these 3 subscripts mean 3 different things. So it's extra confusing, but just remembering that 3 different things means I can actually remember what they mean. And so you can make sense of what it means to be compatible, or you can show that these are all connected, and that's how you do it. That's Proj. And I should say that our condition that S plus is finally generated, so if it's generated by these M things, for example, then that implies that Proj S is the union of these distinguished, and also this is spec. This is an affine thing, which is quasi-compact. You take S dot, you localize it at M, and you have 4 subscripts, even better. And you take the 0th graded piece. So it's covered by finitely many affines, and anything covered by finitely many quasi-compact things is also quasi-compact. So any Proj we get, any affine scheme is quasi-compact, and any Proj is quasi-compact as well. Okay, and so the last thing I want to say about Proj is that when you think cleanly about it in terms of graded rings and not thinking about it in terms of polynomial rings. So suppose you have an n-dimensional vector space. And so the traditional notion of projective space, I think, well, even this is probably not true, is the set of one-dimensional subspaces of a vector space. So if, let's say you have a vector space, it's n-dimensional over a field K, then I want to consider the symmetric algebra not on V, but on V dual. So in other words, you take sim n of V dual, and maybe the weird thing is the dual at this point. And this is a finely generated, I should have meant that, yes, it's n-dimensional. This is a finely generated ring. And so Proj of it is going to be p to the n minus 1. Why? Because if you choose a basis of v of n vectors, then you write down what this ring is. This ring really is equal to k adjoin x naught to xn minus 1 after you've chosen your basis. But the reason for the dual is this, which is if k is algebraically closed, so we can think about things more geometrically, I claim that the points, the closed points of the thing we created are the one-dimensional subspace of V with no basis, no choice of basis needed. So I guess I should say canonical perhaps, which is, so without choosing a basis, there is a basis-free bijection. And so that's a good exercise because I always find it confusing. And then after I'm confused, I'm a better person for it. Okay. So now let me go back to, now that we have examples of projective things, we now can get schemes by just arbitrarily gluing affines together, or we have this machine, Proj, which lets us, with a single graded ring, glue together lots of affines. So let me now discuss how discuss like a really important construction. So my idea is going to be as follows. So the problem is that on the geometry side, if you have a scheme, there's this tension between the geometry side and the algebra side in the following way, which is that if I have spec A, that's on the algebra side, and you spec B, that's on the algebra side. But how they talk to each other is through geometry. Like there's no spec involved here. So, well, the best thing to say is to describe it in terms of some examples. So let me define, first of all, what a complex scheme is, a scheme over the complex number. So I'll call it a C scheme. And it's a scheme all of whose functions are C algebras. So on a complex variety, all the functions on any open set, of course, you should be able to multiply them by the complex numbers as well. And of course, implicitly, I mean, even the restriction maps are maps of C algebra. So everything is, so we have not just a ring space, but a space whose rings are all C algebras, not just general rings. And then the advantage, well, then a feature of this is that I can just replace this by an arbitrary field and do the same thing, or even an arbitrary ring. So I can have schemes, A schemes where A is a ring, and then everything gets put, I'll just search and replace. Okay, so now we have the notion of a scheme not only over the complex numbers, but over the rationals, over the integers. And it's true that every C scheme is a Q scheme because everything that's a C algebra is a Q algebra. It's true that every scheme is a Z scheme. So I'll just mention that. And now let's define some properties. So one way to define a property of a variety or a scheme, I guess we don't know what a variety is yet, is the notion of when it's reduced. And now I'm about to make a laundry list of definitions. And the question you should always be asking is the question of why would you make this definition? And the answer, like, why should you care? And the thing to be careful of is you may think you don't care, but you actually might. You should also be careful about things that you think look important, but actually are not. So let me try to say why things are important. Some things are important because they are always true, but you need the hypothesis. Some things are important because they capture something essential. So the first thing I want to say is the notion of reduced or nilpotent free. And the reason is because this means, as with the questions before we officially started, functions are determined by the values of points. And in the picture, it means that there's no fuzz. The picture you have has no nilpotent extra fuzz. Okay, so now let me make the definition. So reduced will mean nilpotent free. So for a ring, I know what that means. So you take a ring A, you take the nil radical, which are those things whose have some power that's 0. So this nil radical, which is an ideal, you can check that this commutes with localization. In particular, if you localize at any point, you get the nil radical of the localization. So it's an algebra fact. It's completely readily easy to check. And you should almost be thinking always, if you have any reasonable property of rings, you should always ask, does it preserve by localization? And hopefully it will be. But in particular, if the no radical is 0, that's the same thing as all of its localizations at primes being 0. And here I'm using the algebra fact or sheaf fact that we've talked about before, that you should immediately this is something which should be at the tip of your tongue, that a module being 0 is exactly the same as its localization being 0. And you should not just remember it and recite it, you should remember why it's true. So if you don't off the top of your head, you might want to remind yourself. But then that means that the nil radical of the stalk is 0. And so we can now make a definition. I'll say that a scheme is reduced if all the stalks are reduced. And the advantage of this is it's only about the stalk. It's not about any affine opens at all. So it's completely about the ringed space. You don't need, but that means that that's the same as it being reduced for all affine, spec A being reduced for all affine opens, because to check if it's reduced, we just need to check if the stalks. But then you can also just check in your favorite affine cover. The problem with all affine opens is there tend to be a lot of them. Whereas for example, projective space, there's like a certain favorite affine cover we have. And if spec A is reduced, then we can for each in our favorite affine cover, maybe even a finite number, then we know that all the stalks are reduced, which means it's reduced for every affine. So this makes us happy because we like that functions are determined by y. So that's our first definition. Reduced, is that a dumb name? No, I think it's okay. It's not brilliant. Okay, now comes a dumb name, or kind of dumb name. Another definition that's useful is so this basically means, this is like integral domain, the scheme version of integral domain. I guess that's why integral. And one thing about integral domain is its spec has no fuzz and one piece that we've already talked about with the topology. And we say it's integral if every single open set is an integral domain. And so that turns out to be the same as with affines, that it's the same as it being reduced and irreducible. So integral means I picture a ring that's integral means no fuzz and has only one. Okay, next example, unique factorization domains. Again, well, here we have something interesting, which is this is not an equivalence. That if a ring that's a unique factorization domain, any localization is a unique factorization domain, but you don't have something going in the opposite direction. It's possible to have something, all of whose localizations at primes are unique factorization domains, yet it's not a unique factorization domain. And number theorists know about this from the notion of the class group, which is secretly geometric. Okay, so we only have a one-way thing, and we have this unpleasant thing here, but we'll say a scheme is factorial if, and I should say, I secretly think locally factorial, but maybe that's not ideal either. But factorial it really means at the stalks, not affine, not at the affines. So it's factorial if all the stalks are unique factorization domain. And then that's something which you could, in some sense, check on an affine cover. So you just need to check point by point. In other words, what I mean to say is if you have an affine cover that are specs of unique factorization domains, then it's factorial. But unfortunately, because of this direction, you might be worried about, like, if you fail to find an affine cover where the specs are UFDs, it doesn't mean it's not factorial. You just may have failed. And also, there are even really horrible things that there are certain schemes, certain varieties, where every single affine open, none of them are UFDs, yet all the stalks are UFDs. So watch out for those. And an example is, if you want like an actual example, I even drew a picture of the actual example. Okay, another thing another algebra fact are integrally closed, a notion of integrally closed domain, which, just to remind you what that is an integral domain. And it's integrally closed in its fraction field. If any solution to any monic equation where all the coefficients are in your ring, if you have a solution that's in the fraction field, then it must be in the original thing. And the example to keep in mind, if you haven't seen this before, in which case you shouldn't worry about this too much just yet, but just an example to have in mind are the integers. And the rational root theorem says if you have a monic polynomial, all of whose coefficients are integers, then every rational root is integral. That's exactly what this is saying. Okay, and then it's not hard to check that if A is integrally closed, then its localizations are integrally closed, in particular at a prime. And once again, well, now we have an interesting question, which I'll leave open for you to ponder. But let me avoid that question and just say that gives us a definition. Anything about local rings, we can now define a corresponding property of schemes. We'll say it's normal. Okay, that's a horrible name. that it's normal if and only if the stalks are all unique factor. They're all, oh crap, right? I meant this to look like the previous page. Does it look like the previous page? It does. But I forgot to remove this and say if and only if it is integrally closed domain for all p. Right. And then, just as with the previous example, if you find an affine open cover such that it specs of integrally closed domain, then it's normal. But it only goes one way, or does it? Great. And also, any unique factorization domain is integrally closed. The way you prove that the rational root theorem for the integers is by using the fact that you have unique factorization. And that means that every factorial scheme is normal scheme. Okay, so before moving on, there's a question of why do you care about these things? What does normality and factoriality mean? Well, slightly unsatisfying answer is that integral closure is important in algebra, so you should expect it should be something important, and ditto for factorization. But it's something a little bit better than that. One thing in geometry you want to make have a notion for is smooth. What does it mean for a scheme to be smooth? We have this idea of what it means for a variety to be smooth when we draw pictures. And what do you do if it's not smooth? Part of the point of creating this machinery is we now have a language to deal with things that are not smooth. And if they're not smooth, how do we think about them? Well, in mathematics, a constant theme in many parts of mathematics is that if you have something that's not, in some sense, smooth, you resolve it to make it smooth. So you try to sort of resolve the singularities of a differential equation, of a certain kind of geometric space. And these things are, smooth things, once we define them, will be normal and factorial. And so these things are kind of halfway houses on the way towards being smooth. And also the flip side is that one of the ways in which smoothness is nice when you try to prove things is through normality or factoriality. So these are things we will see later on. And then furthermore, if you try to resolve singularities and normal is on its way to being smooth, the first thing you can do is take the integral closure of a ring, and that becomes integrally closed, hence the name. And similarly, there's something which takes you on the way to becoming smooth, which is called normalization. And the content of that, there's no additional content than taking integral closure. Okay, so these are all things you can define. These are all things that are at the level of stocks. Okay, so now comes something which is really, we're going to use lots and lots and lots. And it's really easy to prove. And it's really, you'll see it's powerful. And so the only way things can be easy and powerful is if they're really clever. So this is like a really clever idea. So here's what it is. So the statement, the lemma is the following thing, which is if you have a scheme and you're wondering, and you have some of the affines have certain properties. Maybe they're unique factorization domains, maybe they're something else, but they've got some property that you're interested in. And you know the following two things. You have already checked the following two things, that if spec A has this property, then every spec A sub F has the property. Maybe I'll even tell you an example of a property, just a sample example of a property. One might be it's reduced, A is reduced, or another might be, as we'll see soon, A is an Noetherian ring. Okay, so let's say you know that. And let's say you've also checked that if you have an affine open set, and you have a bunch of elements of the ring that generate the ring. And now I want you at this point to, ideally you cannot help yourself. You see this and you immediately think in the same thought that this means that you've covered spec A with these distinguished opens. That's what this means. That's the algebra and that's the geometry. Okay, and now if everything in this cover has this property, suppose you've checked that forces spec A to have this property. So once you check these two things, then if you've checked on an open cover, your favorite open cover, that those particular specs have this property P, then every single affine open specs has a property P. So like for projective space, once you check the standard opens, you know every single affine open works. So you can check for this property on any open cover. Okay, so let me prove this. maybe I'll give you a chance to digest this. And the proof it consists of basically two pictures. So the first picture is for this lemma, Nike's lemma. So Nike's lemma is the following thing. I guess you may wonder why it's called Nike's lemma. Nike is the Greek goddess, the winged goddess of victory. And some things seem to be named after various mythological beings. You might also see things ascribed to Kisin. And Kisin, you can look up on Wikipedia, is a Mayan death god. And this is the Greek goddess of victory. Okay, but back to the math. So if you have, so Nike's lemma is the following thing, which is if you have X and you have two affine open, so there's my picture, there's X and you have two affine open subsets, spec A and spec B, then I claim that the intersection of these two is covered by open sets that are each distinguished open sets of spec A and spec B at the same time. So for sure, because the distinguished open sets of spec A are a base for that topology, I can certainly cover it with affine opens that are distinguished in spec A. And separately, I can cover it with affine opens that are distinguished in spec B. But this says I can do it with affine opens that are distinguished in spec A and spec B. Okay, so here's the proof. And this is like the one trick is that you're using the fact that you're talking about locally ringed spaces. So the trick is as follows. So let's start off. So what I need to show is that given any point P, which fortunately I've already drawn, I can find a neighborhood, an affine neighborhood that is spec A of sub something and spec B is sub something. So my first approximation is I'm going to just take spec A sub F. In other words, I'll take a distinguished open subset where F, so F is inside A. So what, okay, great. So at that point, that's distinguished in spec A. Okay, inside that, I will now take something which is open, a distinguished affine open in spec B. And so now I've got something that's distinguished in spec B, but I seem to have lost the fact that it was distinguished in spec, that it was distinguished in spec A. However, what is this thing here? This is where, what is this? It's where G doesn't vanish. So in other words, it's where G is non-zero. And in particular, inside spec A sub F, there's some element of A sub F, which is G, which is what G restricts to. And this is where, this is inside here where G is not zero. So it's a distinguished open of this. And you can check that a distinguished open of a distinguished open is a distinguished open. In other words, G lies in A sub F, which means that G times some power of F lies inside A, and that's what you use. So to say it again, the way you find something which is distinguished in a distinguished open of both is you take something that's distinguished in one, and then you take a smaller thing that's distinguished in the other, and then already that's forced to be distinguished open in the first. So that's proof by picture. And now I'm ready to prove the affine communication lemma in general. So just to remind you what it says, it's in the box. So we have a scheme, we have a property enjoyed by some of the affine opens, and we've already checked that if spec A has P, then every distinguished open of it has P. And separately, if you have an affine and a distinguished cover of it, such that the pieces have P, then the entire thing has P. So the conclusion is that if X is covered by a bunch of things which have P, so let's say A1, A2, all the way to A4, for example, if we check that those each have P, then any other one also has P. And so I'll show you that this spec A has P from the fact that each of these covers have P. And how do I do it? I just cover the intersection, there's spec A. I will show you that I can cover the intersection of spec A and spec A3 with opens that have P, that are distinguished, because I can cover this with things that are distinguished in both A3 and in spec A. So I have, and so all of these, this had P, so all of these have P. And similarly, I can do the same thing here, and here, and here. What I've done is I've covered spec A with a bunch of distinguished opens of spec A, each of which had P, and thanks to number 2, that means spec A has P, and that's the proof. So again, proof by diagram. Looking at this diagram after the fact is not going to help you, but hopefully you can go back and think about that. And that's the proof, that's it. But it's incredibly powerful, and I'll give you some examples. So it's true that if A is a Noetherian ring, then so is its localization, A sub F. That's, we talked about earlier, the fact that Noetherian rings are preserved by localization. What's less obvious, but also true, is that if you have a bunch of generators of the ring, which again, you cannot help yourself because you're a geometry person, of thinking that it's thinking what that means geometrically. And if you knew that each of the A sub Fi's is Noetherian, then so is it. So this is going to be an exercise to, you should try to prove this. And again, a good exercise is one that proves itself if you listen carefully. And if you listen to this, how's the proof going to go? It's got to be, if you have an ascending chain of ideals in A, you want to show it stabilizes. And so how's that going to work? Well, that means you must somehow have ascending chains of ideals in each of these. And somehow, if they all stabilize, that should force the original thing to stabilize. So there you go. Go ahead and think about it and see if you can make that turn into something. And once you've done that, we now have a definition. The definition is that a scheme is locally Noetherian. I'll give it the name, locally Noetherian, if every affine open subset is spec of a Noetherian ring. So all you have to check is all the affines in an affine cover. So projective space, an example of something which is locally Noetherian is projective space over a field, because it's covered by polynomial specs of polynomial rings, and they are all Noetherian. And so every single affine inside there is Noetherian. And I'll define Noetherian more generally. A scheme is Noetherian if it's locally Noetherian and can be covered by finitely many affines. And in general, you'll notice there's a definition that's going to be X is defined to be locally X plus quasi-compact. That'll be repeated. Okay, so now we know what a locally Noetherian and Noetherian scheme is. Again, why do we care? It's because Noetherian rings are nice, and we can prove things about Noetherian rings, and things that come from geometry tend to be Noetherian. And it really is true that any reasonable person will only ever see Noetherian things in their lives. And there are some people who are not so reasonable. They are often number theorists, and they will have to deal with things that are not Noetherian. Okay, another algebra fact. So there's a notion of, if A is an algebra over a ring, or a field, say, you have the notion of when it's finally generated over that. And it's true that if a ring is finally generated over a field or something, then so is any localized. So is when you invert F, you have one extra generated. And similarly, you can show, and you should show, this is not immediate, you have to think a little bit, that if you have, again, you have a distinguished cover of spec A, or if you have a bunch of generators of this ring, and each one of these things is finally generated, then so is the original. So once you have that, once you've shown this, then we have a definition. And the definition is that a scheme is locally of finite type. Maybe I should put, whether you should put an of or not, I think is an open grammatical question. So yeah, it's locally of finite type over R if for every affine subset of it's spec of a finitely generated algebra. So finite type will then be locally finite type plus quasi-compact. And some explanation. So for example, projective space, again, it should be nice because projective space is always supposed to be nice. Projective space is, we already know it's quasi-compact, and it's spec of finitely generated algebras over the field. That's what each of the affines look like. So that's an example of a finite type scheme over K. And just maybe one comment on words, which I didn't realize when I first learned these, is I don't know which mathematical culture this is true, perhaps French, that the phrase finite type translates to finitely generated. So often things that are finite type, if you translate them to finitely generated, then you'll see what this means. So this is like locally finite type means, I guess one could say A is finite type over R. A is a finite type R algebra, which means finitely generated. Okay, good. That's what we mean by, that's an example. And now finally you're wondering what a variety is. So let me see if I can tell you what a variety is. So a variety over a field. A variety over a field, okay, it's going to be a scheme. This is not the natural first definition you should see, I should say. So it's a scheme that is finite type. That means that somehow this is like it's geometric. It's things you can visualize in n space. And it's reduced, it has no fuzz. And we're basically there, but then also it's Hausdorff. Okay, but we don't know what Hausdorff is. So I can't tell you what a variety is after all yet. So we're missing only one thing. And then maybe you're angry. maybe, yeah, okay, so you're sad or angry or generally not feeling positive about the world. But I will, however, I will define an affine variety, which is an affine scheme, which is finite type and reduced. And it's a projective variety, it's projective scheme that is finite type and reduced. And the reason I'm allowed to tell you this is because it turns out that the Hausdorffness, whatever it is automatically true. And as a comparison to show this is not a nutty thing for me to say, is that manifolds were first defined as subsets of R to the n. And there was no Hausdorff condition needed because any subset of R to the n that satisfied the other parts of the definition manifold, that was automatically Hausdorff. So it was inherited from affine space from R to the n in general, or RP to the n in general. So and it was only when people began to think about abstract manifolds that they realized they needed one extra thing, which is this Hausdorffness. So that's why I can tell you what these are and why the ancients knew what these were, but then we'll leave it. Okay. I guess some small additional things I want to say is that if you have something that is locally of finite type over K, again, hopefully you've got to take these random collections of words and translate them to geometry. All this means is that it looks like spec of a polynomial ring mod some stuff, finely generated algebra. So it locally looks like that. Then because you know what the closed points of X turn out to be just the closed points of these, and those are, as you already know, that in this case the closed points are those whose residue field is a finite extension of K. This is the Null-Stellensatz in action. So when you're in that geometric situation, something which really looks like classical geometry, then then this is true. And then we already have the definition of the degree of the closed point to be the degree of the field extension. So over the complex numbers, all points are created equal. All closed points are created equal to all degree of 1. But over the real numbers, there are points that are whose residue field is R, and other points whose residue field is C, and the C points count for 2. Okay, so at this point, we have a good sense of what schemes are and some of their properties, and it can be useful to know what associated points and associated primes are. I realize that in the version that's posted of the notes, I don't like I like the philosophy behind associated points, but I don't like the actual content. So I've rewritten that, but it's not public yet. So just skip it. And ditto, if there's stuff on length, you can skip that too. And instead, we can start to talk about finally morphisms of schemes. And once you're thinking categorically, once you say what a scheme is, you're dying to know what a map of schemes are, because you really need to know, otherwise you find you just cannot use the word scheme in very many sentences. So let me motivate the notion of a morphism of schemes by first telling you something which I at least implicitly said in the past, what a morphism of ring spaces is, since our scheme is just a certain kind of ring space. Okay, so morphism of ring spaces is so ring space is a topological space with a chief of functions. So a map between one to another of it should be, well, it's got to respect somehow the 3 different things in the definition. So it's got to be a map of points. That map of points better be continuous. So it's got to be a continuous map. So the topological thing is a property of the map of points. Now you want the additional data of the pullback of functions. And so if functions are determined by the values of points, there's no additional data necessarily here. And this is why this is a bit confusing. Currently, all it is for every open set, I'm giving you a ring. I'm saying nothing special what that ring is. So when I give you a morphism ring space, I need to tell you what to do with that sheaf of rings. And what you do is you have to know how to pull back functions. So the picture to have is that you have a map from X to Y. And I want to say that if I have a function on some open set in Y, I want to know how to pull it back to its preimage on X. So what does that mean? It's literally that you want the data of a map of sheaves from the sheaf of functions on Y to the push forward of sheaves of function on X. Or if you remember that adjointness diagram from a couple of weeks ago, it's a data of, for every open set on Y, a map from the functions here to the functions on the pre-image, and they better behave well with respect to restriction. So if you have that extra data, that's the meaning of morphism ring spaces. And you can check quickly that if you take two morphism ring spaces and you compose them, and they're composable, you get another morphism ring space. And now you can check quickly, and I think we almost largely have already, that if you have a map of rings, you already know you have a map of topological spaces of specs in the other direction, but you even get a map of ring spaces. So the map topologically, you remember, we had map first as points. Prime ideal of A gives you prime ideal in B. Secondly, the open subsets on spec B pull back to open subsets on spec A. How do we know that? We just check a basic open set, and a distinguished open set, spec BG, pulls back to where to A sub pi of G. And here I should say is like the locally ring space part of it. When we throw out where G vanishes, then that pulls back to where G vanishes, pulled back is to where the pullback of G vanishes. That's the meaning here. And then now what's the ring map going to be? What's the sheaf map going to be? Well, for any of the basic open sets, I'll tell you what it is. So on where F doesn't, I guess I should call that G, sorry. Where G doesn't vanish on B, I will now tell you how to pull back the functions on spec B sub G, the functions on spec A sub pi of G. And there, I already have a map from B to A, and that induces a map of rings from B sub G to A sub pi of G. So if you want to write that down. So I just told you what it is. That's a map of rings, and it's on that open set. So we have a map of ring spaces already. So so far so good. And so now I want to make this more precise, and so that's what we'll talk about next week. Let me set us up for next week by saying that already I could tell you a definition. One definition of a map of schemes is a map. So definition one, and this is not what I'll say next week because it's the wrong definition. Well, it's correct, but it's confusing that if you that you have a map of schemes, a map X to Y of schemes can be defined to be a map of ring spaces, which we defined, that locally looks like spec A to spec B, which we've already defined. So in other words, you have a map from X to Y. What I mean to say is that near any point, you should be able to find affine opens, and it should look like this. So what's wrong with this definition? I should say it's a true definition. This is equivalent to the definition that we're eventually going to give. So what's wrong with it is that it's hard to check. You have to check every single affine or just sufficiently small affines. So you could say you could say sufficiently small affines, because if it's true for one like this, you should be able to do some sort of localizing. And then do you have to check on just a cover? And so you could take this definition and use the affine communication lemma, for example, and use that to show it's well defined and you only need to check locally. So this is a good perspective and just a complicated place to start. So, so here's definition 2 to set us up for next time, is that there's a notion, we already know the notion of locally arranged space. And why did we have this notion? We had this notion, which can be because you, or some of you in week about 2, came to the idea that it really mattered that where functions vanish, that should be a closed subset. And that led us to this definition. So this is better than a ring space. It's and schemes are locally ring spaces. So when we get from in this tension between thinking of X as a ring space on the geometric side and a scheme and a spec A and a ring on the algebraic side, the tension between these is that when we want to have maps from one of these to another, getting between these two is confusing. And the notion that will make things easier is locally ring spaces. And I would emphasize before next week that you can use locally ring spaces to make this work, and then you can forevermore, for most people, forget the notion of a locally ring space other than as motivation. So I feel once you've done that, you can just stick to affines for almost everything you care about. And I feel like you should until you're forced to go back to locally ring spaces later on. So, and now I'll say that the problem is if you map spec A to spec B in the way that I told you we want to, that gives you a map of ring spaces, but there are maps of ring spaces that are not of the form we want. And the real punchline is that any map of ringed spaces from spec A to spec B, any map of locally ringed spaces is a map of the sort we want. In other words, all we need to know something's a map of the sort we want is that it's a map of locally ringed spaces. And that means once we check that, I can now define a map from X to Y of schemes as a map of locally ringed spaces. And then for free, it's a map to ring spaces. And for free, every time we have an affine to an affine, it's a map of the sort we want. So what's left for next week is to show that maps from spec A to spec B as locally ringed spaces are the same as maps from spec A to spec B of the sort that come from maps ring spaces of the sort that I explained. So on that note, we're ready to talk next week about morphisms, and so now is a good time to call it a day and see if people have some questions. So if you have to, so this is the official end. So if you have to go, now's a good time. Or you're welcome to go now. Nothing new will come thereafter. I will now switch over so I can see Zoom. Where did it go? I'm getting somewhat scared because it's all silent.
Okay, I'm here. Let me go get a soda real quick. Mineral water. LaCroix. Okay. All right, so we got some questions. Okie dokie. Let me just go look and make sure I'm not missing anything. So the first thing that I had, let's see. And we don't have that many. Okay, so here's a good one. So what does normal mean geometrically?
Great. Okay, the first question is, okay, what does normal mean geometrically? Okay, normal mean geometrically. Okay, so I'm going to answer this question in the best way I know how, which is somewhat empirical. So I'll tell you what it looks like without it being exactly the same. One weird thing about normality, some things are fundamentally geometric and some things are fundamentally algebraic. And often things that are more fundamentally geometric are confusing algebraically, and things that are more fundamental algebraically can be confusing geometrically. And it's the interplay between the two which gives some power to this to algebraic geometry. So normal is algebraic, and then I could tell you how to look at something and see whether it's not normal or not. So one thing about normality is that it turns out that it's always unibranch.
Are you drawing anywhere? I don't know if you
am, and that's
because I can't see it if you are.
Let me see how the sharing is going. How about now? Better
I
now?
cannot see anything that you're drawing.
Let me see. This means I should. Ah, yes, it's paused for some reason. Good. Oh no, pause still. Now it should work.
Okay, great. Yeah, that's great.
Great. So it's I don't know how this could ever work without having people, not just the one person doing the drawing and not having people.
I mean, and on TV shows they have tons of producers and stuff, you know.
That's true. And they're always very they're okay, you're all assistant producers then.
Yeah, exactly. We're producing this.
Yeah. So great. So if something is not unibranch, And I know then you're going to ask what unibranch means.
Yeah, what does unibranch mean?
I'm not going to tell you because I feel like, no, I'm not going to tell you. It then becomes, so there is a reasonable thing, but then it's going to add definitions upon definitions. But the definition is trying to abstract from your notion of that there. So what it should be, something which is not unibranch, means that there's something that separates the branches that maps to it. And so that's a possible definition. But that's not a great definition.
What does normal mean for curves?
Great. Normal means, thank you. Normal means smooth. And you'll say what a smooth means for curves, and I'll say normal. It means that's the same as factorial. What's a curve? Well, a bit of a curve is a discrete valuation ring. And in dimension one, okay, what's dimension? All the questions, once you start asking one, you're forced to ask lots and lots. So something which is dimension one and smooth is the same as dimension one and normal, or dimension one and factorial. So if you've learned about discrete valuation rings and you've seen this fact about discrete valuation rings, that if you have a Noetherian, I hope I get this right, dimension one, maybe in a world domain, then all these things are the same. Integrally closed equals factorial equals, okay, I'm already run out of ideas. There are around 7 different equivalent things. So that means that for curves, all these things are the same. So in particular, normal means what you would think of as smooth. But for surfaces, that's not true. So that's the weird.
What are Serre's criteria?
Yes. So Serre's, so it turns out that Serre, I don't know. I just named it all.
Serre again, right? Serre strikes again.
It's always Serre.
It's always Serre.
So one thing, which is another way to recognize normality, is it also means that it's at least smooth in codimension one, which is related to this fact that in dimension one. So what do I mean by smooth in codimension one? It means the singularities are higher codimension than codimension one. And again, what does dimension mean? I'm not telling you, but it's what you think. It's what you're picturing is correct. If you picture something and you see something which has 2 pieces that, well, actually, that's already not unibranch. But let's say it looks like it's unibranch.
Cone point is a good one.
What's that?
A cone point or something.
Yeah, a cone point is great. Okay, that's codimension bigger than 1. So normal means smooth in codimension 1, implies smooth in codimension 1. So that's one way of empirically saying, oh, that's not normal. And but there are things that are smooth in codimension 1 that are not normal. And there's this criterion called S2, where S is for Serre and 2 is because he's too good. Serre's S2 criterion, that if you have regular codimension 1 plus Serre's additional criterion, then it's normal. And in particular, you can check this at every point. And so this really becomes a local criterion. So I'm not going to tell you what that is either, except that it's part of the definition of Cohen-Macaulay, which I'm not telling you what that is either. What's
something that's not Cohen-Macaulay?
What's that?
What's the first drawing that you think of something that's not Cohen-Macaulay?
Okay, I feel like this may not be super helpful because you're not going to because you don't know what Cohen-Macaulay is. But if you have a bunch of things,
I knew it. That's what everyone draws.
Things of different dimension, right? Cohen-Macaulay means things are equal dimension, but we don't know what dimension is either. So
yeah. Okay, so let's move on to normality or Noetherianity. So why did we not define something being locally Noetherian as a stalk-local property?
Right. So another reasonable definition would be if OX comma P is a Noetherian ring for all P, then this is not the same. Well, it's implied by, but it's not the same as that it's a Noetherian scheme. And so they're not the same notion. And I guess you're going to ask me for an example.
I couldn't think of one. I didn't know. Yeah.
Well, the problem is it's hard to think of an example of a non-Noetherian ring without practice to begin with.
I knew I can do non-Noetherian rings, but one that is locally Noetherian, or I mean stalk-local Noetherian, but not Noetherian.
Right. Let me think.
You just put a bunch of infinite number of variables, and then that's one way to get a non-Noetherian ring.
The first example, I thought it was Q bar, tensor Q bar.
That is good.
Because
Okay,
that's
I mean,
totally disconnected with infinitely many components.
so this is an amazing, I love this ring. Yes, this is an amazing ring. Yes, and this is something which is, if you're a number theorist, Q bar, who doesn't like Q and Q bar? This is like some of the most amazing things that mankind has ever seen. So this is not beyond the pale. It's not pathological. It's not something you would never see. And so this ring is, as Jonathan says, this thing is not Noetherian, and it is also, but all of its stocks are Q bar, I guess, right? Is that yeah? So all the stocks, OX, like all the stocks turn out to be Q bar, which is certainly Noetherian. So that's why they're not the same. And then a related question is, well, then which definition is the right one that deserves a name? Like, which is the one that we should remember and use a lot? And it turns out that the right notion the right hypothesis that will be used, that will imply lots of useful things, is for the thing to be Noetherian, not just for the stocks to be. So these are not the same. It's hard to think of something which is not the same, or they're not the same, and it is, and that's why the notion is this one. I mean, knew what she was doing.
There's a kind of another version of this that maybe is more down to earth, where you take the direct limit, you take the stock at every point simultaneously. So you take the direct limit of all the open subsets, all the neighborhoods of all the points simultaneously, and you get this totally disconnected union of.
So you're telling me that's going to be that's more reasonable?
Well, you don't have, it's just the Zariski topology. It's not,
Isn't that
you don't have any Galois theory tied into it.
True. So from one point of view, it's better. Yeah, great. Depending on your metric.
Yeah. That's from Bott and Schulze from the Proj topology, that construction.
The other thing.
Yeah.
The other construction, taking something and right. So what you're doing, right? It's a neat thing you're doing. Like, this also tells you about Q bar over Q, because it somehow takes this thing which is just spec of Q bar is a point, spec of Q is just a point. But by doing this, a lot more information becomes clearer. And similarly, what Bott and Schulze are doing are taking your space and kind of exploding it into these pieces, which somehow can be easier to work with as well, but at the price of non-Noetherianity.
Okay, so here's another question. So if you take a map of sheaves, you've got a map of schemes. You have the associated map of schemes, or the sheaves, excuse me, structure sheaves, right? Where, say, if you have X to Y, then you have OY going to the push forward of OX, and you can use by adjunction, you have another map. You could have defined it this way, right? And so when is this other one useful?
I guess I cannot help myself from not being able to see the difference between these two things often. I do secretly, if you know about these quasi-coherent sheaves, so if this is, I will say that let me give two contradictory answers to this, two different answers. The first is that I can't see any difference between these two. When I see the other, and I really see the third one, which is for any open set in Y, set an X mapping to it, I see the map from functions here to functions here. That's the same. They're all the same information by adjointness. But of course, the point of doing this is you can flip back and forth and take the one that's more advantageous. I'd like to make one case for why this is more advantageous. And the reason this is a bit more advantageous for me, in one sense, is that if you have, I'll tell you in general, let's see, let me do it this way, that if you have a ring and you have a module, then corresponding to that, you have spec A and spec B. And let's say you have a ring map like this, and you have a map of schemes, and you have this sheaf M twiddle, which we've already defined. And then if you were to push forward M twiddle, I can tell you what that is. That thing is going to be, well, M is an A module, so it's also a B module because B acts on A. So in fact, you just take M as a B module and take its twiddle. So push forward for modules is really easy. So the push forward of OX is just going to be A as a B module. So if you want to think about it in terms of these twiddles, push forward is a better thing to do. But if you want to think of functions as having values of points, this is the better thing to do because you would like take your function and you pull it back. I don't know.
I think stocks are easier on the second one, right? So
Yeah, so if you like thinking in terms of stocks, if it's more advantageous at that moment to use stocks, then the second one is better. But the problem with this stock is you get it's a sheaf on the topological space, but it's not immediately an OX module.
Yeah.
No, actually, it is an OX module. Sorry. Oh no, sorry. This will okay. Let me. I'm going to confuse myself. I think too much out loud. Yeah. So that's why I said it this way. But really, this thing doesn't look like functions anymore. You pushed it forward, whereas this pullback looks kind of like functions. So I see advantages in both with both, and I did deliberately choose to that one incarnation. But really, the incarnation is functions pull back to functions. Tell me how functions pull back. That's the meaning of this map. And there is something called pi upper sharp, which is one of these two things. And I forget which of the two it is. That's another reason why. Like, is it supposed to be, is it downstairs?
It's supposed to be the top one, but I guess they're
you think it's the top
same,
one?
really, right? So
right, except that it is one and not the other.
maybe you should call the other one pi lower. No, I don't know.
Well, the one up top should be pi lower.
The other one doesn't have a name. Like or does the other one have a name?
I don't know. I forget.
Jonathan, does the other one have a name? Oh, sorry, he's not. He's gone.
So sorry, I'm in the chat.
Yeah.
Right. Great. So one of these is called pi upper, and I feel like maybe that should be the lower one. It is the upper one, I think. But
it is the upper.
It is the upper, I think.
It is the upper one.
Oh, good, great.
Yeah,
but then somehow, if you want to give them both names, you might call the one upper. The upper one should be lower. And okay.
Yeah.
So that's why. Not really a good reason. You have to pick one, and they're all equivalent.
Okay, so another question that I forgot to ask with the normality question was, what's the geometric meaning of being factorial?
That's a harder one. I don't really have a good picture of that.
I don't know.
Yeah, so it's right. That's even more algebraic. Like it's handy because it gives you normality. So it's something which can give you geometric information. Actually, here's a fun fact that if you were to take C adjoin x comma x1, x2, comma x3 up to xn, and you mod it by x1 squared plus x2 squared up to xn squared, then it turns out, actually I even put an m here, but then it turns out that you can quickly check that it's reduced if n is 1, it's not reduced because you have C adjoin x1 minus x1 squared. So it's reduced once you get to once n is bigger than 1. If n is at least, right, so if n is at least 2, it's reduced. If n is at least 3, it's irreducible.
This is a great segue for the next question.
Great. And if n is 4, I'm going to have a hard time drawing this because it's going to be a threefold with some singularity, then it is, if n is at least 5, it's has unique factorization.
What?
Is that right? Am I off by 1?
No, I don't know. I don't know this one.
No. But not when 4. With 4, it's not true because I could change coordinates over the complex numbers and take C adjoin W x y z mod WZ minus XY. And then at least intuitively, WZ factors in 2 different ways. So if n is at least 4, then what's true? What starts being nice there? Okay, actually it's normal here too, once you're at least 3. So that's great. So there's this, so it's, it's also regular in codimension 1. Yeah, so there's this whole, so that's an example of how some algebraic things can be somewhat both mysterious geometrically, but they must mean something geometrically. And in fact, well, you don't get any bonus points for guessing who was able to who figures these things out of how to understand, turn the algebra into geometry. But the proofs of all these things are actually not too bad. Like, for example, they're in the Rising Sea notes variously in various parts from go through it as to why unique factorization happens.
Yeah. So the question that was leading to this, and maybe it is Sarah's fault, is who's responsible for this reduced irreducible integral?
I feel like that has to be, like, if I, okay, you figure out who to
But
blame.
it's in French, so it's maybe it's an English thing. I actually, what is,
I might blame, I wonder, or I might even, like, I feel like it depends on the decade who to blame. And maybe this means the Italians should be blamed if it were in the, I don't know. Yeah, the irreducible, reduced. Yeah, I don't know who to blame for those.
yeah.
I guess irreducible kind of makes sense.
Irreducible, no, irreducible should be topologically irreducible, and integral should be irreducible.
Yeah, I have to think about the difference between those two notions. I don't know what topological irreducible
You
means.
can have like multiplicity, so
Yeah.
it should be, it should be irreducible, is that you don't have any multiplicities, you don't have
That seems reasonable. That seems
factors. Yeah.
I feel like Sarah tends not to be fully at fault for, he bears responsibility for flatness, but the things but everything else, he's given so much to the world that I think. Like,
I was looking at it, he had 272 math sci net.
That's it.
Well, if you look at like Ken Ribbit, I looked at his the other day too. He's at like 72. So it's like, I mean, those are a ton of papers.
That's pretty good. Like Ken Ribbit is like a quarter of Sarah. That's pretty impressive. That's like a that says a lot for Ken Ribbit. That's
yeah. So I mean, no, they're both. I mean, yeah, amazing.
Yeah, Sarah's Sarah. I mean, there's no.
Yeah. Okay. Another question we got was, are you going to do more homework assignments?
Yes, I should. I will. I even for last week, some I meant to put up. So I'll put up some more. I even may try to put up some for sort of, in some sense, the future, in case I don't get a chance to do them in advance. So if the interesting things to look at. So I do intend to do that.
Okay, and I think that's it. Unless Jonathan has something else that he caught that I didn't.
No, nothing here.
I think I have. Let's see. There might be one. Let me see. There's one more. Let me see if there's.
I mean, there was a cool observation that Jonathan made, is that these stock local properties are really sheaves in valued in truth values, in the category of truth values. And I'd never seen this.
Stock local. Wait, but even the affine local can be seen as zero sheaves. Like the fact that so actually that's okay. There's some danger in going down.
Maybe it is affine local and stock local.
No, both. I think you can see all
But
these
they're different. Then they have to be sheaves, different types of sheaves. Then, huh?
Different topology.
No, it's just the affine local. Stock local is actually, this is another question that people are asking. Like, which one is the right way of defining things? Stock local.
You need both of them.
Or affine local.
So one thing I'll say is that affine local is, so stock local is, so it is important to keep them separate for the following reason, which is that stock local is about geometry in general. Like in any geometric category where you have Eulerian spaces, you have stocks. And so it often is very useful to think of those are geometric things. Rings, that's in the algebraic geometry in particular. There's no real analog. And so if the things that are more algebraic, it's better to go with rings. And often with rings in algebraic geometry, if you can go with the specs, it does empirically tend to be much easier. Cohomology is much easier. Lots of things are much easier because they're just statements about rings. So if it is algebraic, often if it's an algebraic notion, often it's better to go with the affines. And if it's somehow a more geometric notion, even if you can write it in terms of rings, it can be better going with stocks. That's an opinion, not a.
I think if you're going to set up the theory, though, like as far as definitions go, going stockwise makes it so that you don't have to check compatibility between open sets. So like if you have something and you can prove that it's a stock local property, then it automatically applies to schemes. I mean, yeah.
So here, right. So here's where I think I believe traditional wisdom is wrong for the following reason: that if you try to make everything stock local, like with the affine communication, it becomes extremely easy to check lots of things. Whereas if you try to do things stalk-locally, you suffer a lot. And for example, showing the structure sheaf is a sheaf can be, in some sources, people suffer a lot when you try to read why it's a sheaf. So I think the reason often definitions are given stalk-locally is because people come thinking geometrically. The notion of a quasi-coherent sheaf is needlessly complicated outside when you do it just purely stalk-locally. It's important to do it.
That sounds like, that sounds like not a good idea.
Yeah, my feeling here is that the properties should always be defined. There exists some open cover where the property holds, or it holds in a neighborhood of a point rather than holding up the stalk.
Right.
That's much more flexible from a sheaf perspective for then gluing these properties together. And
right.
Sometimes if you demand a property at a stalk, you can push it out to a neighborhood, and sometimes you can't.
Right. And the ones you can are the ones that often, well, no, even they're not often. Factorial is not actually.
Yeah, or Northerian.
Yeah. Oh yeah, Northerian is that.
So we're just discussing.
Oh yes, exactly. Yes, good point. So, and being too picky about what your points are. This may be again a more Jonathan-related point than geometry-related point, but you have to have points. You have to know what your points are, and even for complex varieties. A good example would be complex varieties. Over the complex numbers, if you think of them as varieties, you have certain points. And if you think of them over schemes, you have generic points as well. But the open sets are all this. But the open sets are all the same. So you suddenly, if you do it affine by affine, there's no difference between those points of view. Whereas if you do stalk by stalk, you might wonder. It's but I don't mean to, like for complex geometry, you can define quasi-coherent sheaves more generally. Not just, and they just happen to be easier when you have rings to hang your hat on. So I don't mean to diss stalks too much. Although I do think Jonathan's point of there exists an open set near in which it behaves, which the property holds, that's the right way to think about quasi-coherent sheaves, quote, stalk-locally rather than affine. But if you have nice open, it's like, one last thing before I'm beating a dead horse at this point, but when you're thinking about manifolds and sheaves on manifolds, you don't want to forget that balls exist because you do all local calculations on, right? You don't want to say, now I define a manifold, often it's easier to do constructions on contractible open sets. So it's entirely reasonable not to want to forget the balls. And maybe you're even happier that you're living in this world where it's true the intersection of two balls is not a ball. That's annoying. And it's true for a scheme, the intersection of two affines is not always affine, and that's annoying. And if you have this fact that you're living in a ring space that provides bookkeeping for gluing, that may make you happy. But definitely, often it's useful to think about contractible opens, which means balls in the topological setting or affines. Scheme setting.
All right. I think that's it, unless anyone has anything else to add, but I think Jonathan said he doesn't, so I think we're done.
Great. Well, thanks, everyone. So I'll try to get some homework up. Maybe I'll try to do something fast and quick, as opposed to more thought out and hence more delayed.
Yeah. All right, thank you. You got a lot of things in the chat here, too.